Hello all, I welcome you all to this session of turbo machine. From last few classes we are talking about hydraulic turbines. As we discussed, hydraulic turbines are those in which the fluid energy is converted into mechanical energy. Till now we have seen such devices like a Pelton wheel where the flow is tangential, and then we talked about Francis turbine where at the entry of the turbine the water direction will be radial and at the exit it was axial, and we also differentiated between Pelton and Francis turbine by a Pelton turbine is an impulse turbine, and whereas the Francis turbine is a reaction type of a turbine, where in case of an impulse turbine the energy at the inlet of the turbine will be purely kinetic energy, whereas in case of a reaction turbine at the entry of the turbine the energy available will be pressure energy as well as the kinetic energy, and as the water flows through the turbine blades the pressure energy changes and you have in turn you will get the mechanical output. So that is what we have discussed till now. Now whenever we want to choose a turbine for a given site, what we look is that we look for what is the available head, then what is the discharge. Depending on that we are going to select which turbine to use. Now if you have a very high head and low discharge, in that case what we do is that we go for a Pelton wheel. A Pelton wheel operates at very high efficiency at higher head and lower discharge. Similarly, when it comes to a Francis turbine or when you have moderate head and moderate discharge, we go for a turbine called Francis turbine. And then when you have higher discharge but the head is low, we go for a device or a turbine which we call it as Kaplan turbine or propeller turbine. Now when you have higher discharge, like you have a reservoir but the head is very low, in that case the suitable turbine will be a Kaplan or propeller turbine. After all, this is also a reaction turbine, that means due to the change in pressure you have the energy. Now how is it different from that of a Francis turbine? In this case the entry of water to the turbine will be in axial direction as well as the exit is also in the axial direction. That means this is a pure axial machine. Unlike what a Francis turbine where you have the water will be entering to the turbine in the radial direction and the exit will be in the axial direction, that we called it as what? Mixed flow turbine. Now this is a turbine which is named after Victor Kaplan, who is an Austrian engineer for his contribution in development of this particular turbine. This is the modification of the Francis turbine, where you can see that this is the scroll casing what we can see. This is the cut section of course. You can see in the top view where the water will be entering here. Here the diameter will be higher. As you go here the diameter will be lesser. What we want? Because of this we want the velocity throughout the periphery of this turbine should be same. That means as the water enters here and go across this periphery, the velocity at each entry of this guide vanes should be same. We want to keep the velocity to be same, that's why what we have a reducing cross section that ensures the velocity to be same throughout the periphery. Now that is what we are trying to show. This is the cut section. If you cut it here, this side you have a bigger diameter and this side you have a relatively smaller diameter. Now you have guide vanes here, okay. Now the water will be entering in this direction, that is quite similar to Francis turbine as we discussed. Throughout here, this will be water will be entering across this periphery. So here what we are trying to show, the water is entering through the guide vane, or what we call it as fixed vanes. Now these guide vanes will do two works. One is that this can control the flow, that is, if you change the angle of the guide vanes, you can vary the flow rate happening within these gaps, okay. If you change the angle, what will happen? If you change the angle, the area between these two vanes will be lesser. In that case, for example, if you want the power demand is low, in that case you can lower the flow rate so that the energy produced or the electricity generated will be low. So this is doing two works in fact. One work, as we said, this is controlling the flow rate, and it is also controlling the whirl which is created by this scroll casing. So if there were no guide vanes, the whirl action would be dominating. So guide vanes are controlling two things. One is that it can control the flow rate, and it can also control the swirl action. Now as the fluid enters here, if it was a Francis turbine, or imagine that if it was a Francis turbine, this runner would be in the same plane as that of the scroll casing, because of which, just imagine if you shift this up here, the fluid will be entering in radial direction. Now what is the change? We have shifted the runner a bit below, so that after entering, the flow is happening to be in axial direction. That means we have shifted this runner a bit below so that water enters to the turbine in the axial direction, okay. Now water enters here, these are the vanes. Now this total what we are calling it as runner, and we are trying to represent that runner here with a bit bigger picture. Now this is runner. Now this has got blades. Now this is what a blade which is twisted from its root to tip, and it is pivoted to the boss or hub. We call this as boss or hub. Now in case of a propeller turbine, these blades are fixed, okay. Whenever these blades are fixed to the hub or boss, we call that as a propeller turbine. The only small change between a propeller turbine and a Kaplan turbine is that in Kaplan turbine, these blades can be moved, okay. These are generally moved automatically by a servo mechanism, so that at all flow rate water enters without a shock. So a Kaplan turbine is where these blades can be adjusted, the angle can be adjusted, whereas a propeller turbine is the one where these blades are fixed. It is called as propeller turbine because this is an aerofoil, okay. This looks quite similar to propeller of a ship, that is why it is also called as propeller turbine. Now typically these turbines will have 4 to 6 blades. Now you know that when do you change the angle of the blade? Whenever you have higher discharge, these will be getting themselves vertical, okay. Whenever you have low discharge, the tangential component will be higher. So after extracting the energy, it once again leaves the turbine axially. Now we know that here the kinetic energy will be higher, we do not want to waste it. So there is a draft tube which connects the exit of the turbine to the tile race, and here we also know that the pressure energy will be lower, that also will be increased as it moves along. Look at the discharge through the turbine. So it is entering here and leaving here. Q can be equal to area into velocity, right? Here that can be said as flow velocity. Area is what? Only this is the area. I mean, if you look at from the top, this circle is, the inner circle is boss or hub, then the outer circle will be tip diameter, we call it as, that is capital D, this small d is boss diameter, then the remaining area is where the water is flowing. So that will be d square minus small d square by 4 into Vf, where d represent tip diameter or hub diameter, tip diameter, where small d represent hub diameter. Now what we will see? We will see the velocity triangle for the Kaplan turbine. Now let us draw the velocity triangle for Kaplan turbine. We start it at the inlet triangle, that is inlet velocity triangle. We start it from a point where we write the absolute velocity V1. Okay. Now the horizontal component of V1, the horizontal component of absolute velocity, that is, we called it as VU1. Okay. Now the flow component of this, or the vertical component of this, we called it as flow velocity Vf1, which has to be in this direction as we discussed. After all, Vf1 and Vu1 are the component of the absolute velocity V1. Now if you have tangential velocity u, which is greater than Vu1, then you have velocity triangle quite similar to this. Okay, this will be VR1. Now we are interested in what? This diagram is quite similar, or this velocity triangle is quite similar to the one which we wrote it in Francis turbine, because we may be thinking like, since it is an axial turbine, V1 should be equal to Vf1. However, there is a whirl velocity, that Vu1 which we talked about, there is a whirl velocity as the water enters the turbine, and there is a blade angle. So in order to take that, we have the component of V1 as Vu1. So V1 will not be equal to Vf1 in the inlet velocity triangle. Whereas in outlet velocity triangle, now how did we write outlet velocity triangle? We will just first write the regular one, then we will try to convert it. Now this is the absolute velocity at the exit, then you have the components of horizontal component of this, which we called it as Vu2, then this is the vertical component of this, which we called it as Vf2. Okay, then U2, you get this point, this is Vu2, this is U2. Now this will be what? VR2. Okay. Now this is the general velocity triangle. Now we, in order to convert it to velocity triangle of a Kaplan turbine, we know that it is a axial flow turbine. That means flow at the exit is purely axial. That means there is no whirl at the outlet. There is no whirl at outlet. That means VU2 is equal to 0. If VU2 is equal to 0, this V2 line collapses onto this point. Therefore, there is no component of VU2. Now, if you modify this, now this will be the velocity triangle what you have for this of course should be in the same direction as of U here. Now U2 should be from here to here, then this is Vf2. Now V2 is equal to Vf2. Now remember, there is no VU2 because there is no whirl velocity at the outlet. It is purely axial. Unlike in the inlet velocity triangle where you have to take it into account the VU1 component. Now here there is no VU2 means that line collapses to here, which is nothing but Vf2, which will be equal to V2. And of course this U2 and U1 will be same. This is to note that U1 is equal to U2 and Vf1 is also equal to Vf2 in case of a Kaplan turbine. Now there are quite few formulas which we need to note down, that is tangential velocity of blades based on tip diameter, which we denote it by UD, okay, where UD is equal to pi square root of 2gh, where pi is speed ratio, then we can also talk about the value of d by d, where capital D is tip diameter or outside diameter of runner, that is you can see it here, capital D, which we have already noted down. Capital D is the tip diameter or outside diameter of the runner, and small d is the hub diameter or inside diameter of runner. Now this ratio d by d can vary from 0.35 to 0.6. This is the range within which this ratio will be there. That means the ratio of diameter of this to the diameter of the tip or the outside diameter will be from 0.35 to 0.6. Now similarly we can talk about the flow velocity. Vf is equal to psi root 2gh, where psi is flow ratio, psi is flow ratio. Now once again the value of psi will be from 0.35 to 0.75, okay. And lastly, we already discussed this, discharge will be equal to what? Area into flow velocity, where area we discussed pi d square, that is the tip diameter, minus small d square, that is hub diameter, by 4 into flow velocity. Now we have an expression for flow velocity, substitute it here, we get Vf is psi into square root of 2gh. Okay. Now what is important to note here? The u1 will be equal to u2 and Vf1 will be equal to Vf2, and then remaining terms, and also in the outlet velocity triangle know that the wheel velocity component Vu2 will be equal to 0. Now we will solve few problems on Kaplan turbine. Now let us read the problem once. A Kaplan turbine produces 80,000 horsepower. He has given it also in the metric unit, that is 58,800 kilowatt. So note down the data. So power is given in kilowatt, 58,800 kilowatt. Okay. Under a head of 25 meter. So this, as we discussed, Kaplan turbine is a turbine which is used in low head and high discharge. So generally it can be from 4 to 70 meters. So now it is operating at 25 meters. Now which has an overall efficiency of 90%. So is also given overall efficiency as 90%. Then taking value of speed ratio is 1.6 and flow ratio psi he has given it as 0.5. Hub diameter is equal to 0.35 times the outer diameter, that is hub diameter or boss diameter is small d is equal to 0.35 times the outer diameter, or you can say d by d is equal to 0.35. Now as we discussed, the ratio of d by d is around 0.35 to 0.6. Now this is given 0.35. Now what we are interested in finding out? Find the diameter and speed of the turbine. That means we are interested in finding out the capital D and speed of the turbine. Now looking at the data, what we can find out? He has given you overall efficiency and also he has given you the power. Now we know that efficiency is given by what? Output by input. Now here output is what? The power, 58,800 kilowatt. Now if you want to keep it in watt, it should be what? 1000. Because if you are keeping input power also in watts, that has to be cancelled out. Now input power can be written as rho q g h, that is, now this is in watts, remember. Now the denominator also has to be in watts. Let us see. Density is in kg per meter cube, discharge is in meter cube per second, gravity is in meter per second square, and head is in meter. Now meter cube get cancelled out, and then you have kg and meter per second square, that is mass into acceleration, that will be what? Newton. So this is Newton. Kg into meter per second is Newton, meter is there and second is here, that is nothing but joule per second, that is watt only. So the unit what we are talking is right. Now this has to be just solved. Overall efficiency is given, which is 0.9. Okay. So 58,800 into 1000. Density of water which we are talking about, that is also 1000 kg per meter cube. Discharge which we do not know, we will keep it as it is. Then 9.81 is G. Then head. Head is the water available, you can denote it by capital H, 25 meter. Now we can calculate the value of Q. Now the value of Q is coming out to be 266.4 meter cube per second. Okay. Now what did we get? The discharge is 266.4 meter cube per second. Now use this value of discharge. Let us see, can we find out something? Q is given by what? Pi d square, that is outer diameter or tip diameter, minus small d square or hub diameter by 4 into flow velocity. This is what we had done. Now we know that flow velocity is given by what? Flow velocity is also given by psi into square root of 2gh. Now look at what we can find out. Discharge is known to us. This d square is not known, of course, into the value of psi is 0.5, then 2 into 9.81 into head available here is 25. Now here, of course, there are two diameters which we need to worry, otherwise we cannot solve it. Now what we can do, we can take one diameter common, so that we have the ratio, of course, d by d we have, so that we will make use 266.4 is equal to pi, we will take d square common out here, then what we will get here is 1 minus d square by capital D square, of course this 4 is already there, into 0.5 square root of 2 into 9.81 into 25, or you can simply substitute the remaining values. Pi d square 1 minus d by d whole square, you can call it as, we know that d by d is 0.35 square into 0.5 square root of this value, we get the value of capital D. Capital D is coming out to be 5.91 meter. Capital D is 5.91 meter. Okay. Now we also know what U is given by phi into square root of 2gh, where phi is the speed ratio. We know that value, phi is 1.6 into square root of 2 into 9.81 into head is 25, you get the value of UD, which is 35.44 meter per second. Now the value of the tangential velocity we calculated. Now this same equation, I mean UD is also equal to pi d n by 60 tangential velocity. Now UD you have calculated 35.44, pi d we already know 5.91, RPM is what we are interested in calculating, divided by 60. Now you calculate the value of n, which is 114.5 RPM. Now this is what he has asked you. Find out the diameter and speed of the turbine. The diameter of the turbine is 5.91 meter and the speed of the turbine is 114.5 RPM. So in the next class we will try to solve few more problems on Kaplan turbine. Thank you.